My student ID is 0370365, and I'm the leader of this group. Let's begin the presentation. This is our group member, as you can see. And the table of contents starts from introduction to conclusion. Let's begin the introduction. The ultimate goal of this project is solving the energy problem related to SDG 7 and IR4, which is Fourth Industrial Revolutions, using mathematical principles. And then we chose two mathematical principles, which are inclusive and exclusive principles, and some important rule. Briefly explaining the SDG 7 is plans to ensure sustainable energy access by 2030 and to diversify energy sources and increase energy efficiency. And our statement is that reducing environmental problems by optimizing energy consumption of household electronics such as washing dishes, microwave, like that, through discrete mathematical principles. And that's why our title is Optimizing Energy Efficiency in Household Appliances.
My name is Rehana, student ID 0347. So, in the face of growing population and limited resources, optimizing energy consumption is a global priority, especially with the Sustainable Development Goals, of which number 7 is to ensure access to affordable, reliable, sustainable, and modern energy for all. This literature review examines how these concepts in discrete mathematics can be applied as innovative methods to analyze energy use and enhance efficiency. These existing works here touch on each of the research focuses I mentioned just now. The first paper by Morimoto proposed a system to find the optimal combination of appliances under the limit of available power that controls the amount of power supply. The next paper by Kim et al. Discusses 3 energy models. These ones here: physical-based, data-driven, and hybrid, and also model predictive control. The final paper by Zadi proposes combinatorial options to bid for energy and considers social welfare as a factor, so it's completely in line with the goals of the SDGs. The limitations of these works include the following: computational complexity, in which scaling is inefficient and expensive, as well as integration with existing systems. It's difficult to maneuver as there are many interconnected parts of it. Future directions here are possible hybrid optimization models. It combines discrete mathematics and machine learning to predict patterns to adapt to, and then policy and market design. It helps inform evidence-based energy policies from the government and market level. Lastly, for the literature review is how we would differentiate our work from the rest. The works I've mentioned before all focus on optimizing individual aspects rather than a whole complex system, and don't consider the numerous interactions between those components. Our work implement the inclusion-exclusion principle and some important rules together to allow analysis for overlapping demands and combinations for more comprehensive optimizations for complex processes.
Hi everyone, this is Jukman 03801. Okay, let's move on to the methodology and the result part. So, when we look at the inclusive and exclusive principle, EIE is a counting technique to determine the number of elements that satisfy at least one of the several properties and ensure elements satisfy multiple properties are not double counted. When we look at the Venn diagram, we can see two techniques over here. The first one is set A union to set B. It basically include all the elements in set A, set B, and in both. And the second technique is intersect to D. is basically number of elements in the description of set A and set B. And we went through and get some data information online. We assume that the solar and wind energy, the renewable energy can produce 800 to 1,200 watts per hour. And when we look at the electronic appliance like ceiling fan, which can consume around 50 to 100 watts, that's basically suited for renewable energy. But when we look at the coffee maker, which can consume 800 to 1,000 watts per hour, and that device can be used in both renewable and non-renewable energy. When we look at the result part, we can see a two set, the R and N. R stands for renewable and N stands for the non-renewable energy. When we look at the union technique, we can see we collected all the electronic appliance here, and the intersex is only coffee maker because it is under the R and under N. So the conclusion is that we use this technique because it shows us which electronic appliance is suited for which energy. Like maybe ceiling fan is suited for renewable energy and clothes dryer is suited for non-renewable energy.
Hello, my name is Yan Xue. My student ID is 0371927. And talk about this sum and production. Sum and production rule is used to calculate the probabilities of various events. Assume patience first, so you can see there the kettle is used 3 times a day, the washing machine is used 2 once a day, and so on. And we can clearly say you can consume patience there and calculate the total daily power consumed patience. And you can see here is 8 times 35 1 day.
Hello, my name is Shani Hao. My student ID is 036693. Next up, we need to talk how to slow faster power. We have one system adjust cooling jet in the refrigerator to avoid unnecessary power consumption caused by too high energy. In air condition, we have two methods. Running 26 silent. We ask the room temperature down to turn off this internet when sleeping. Then get totals 7.6 units 1 day. After optimization, 0.75 units can be saved every day, which is 13 times 0.75 into 2.5 units per month. This combination helps us determine optimal shopping method.
To sum up, we will do the conclusion. By using sum and product rule and exclusive and inclusive principles, we have developed the strategy to lower cost and improve energy efficiency. In the end, this leads to economic savings and environmental benefits. Finally, this contributes to Sustainable Development Goals 7, which is SDG 7, which will ensure affordable and clean energy access by 2030. References. Thank you.